frontier. So as you've probably noticed, Hurricane Sandy is on its way, possibly past by the time you watch this video. And we're going to pretend you're the manager of the call center for the National Grid, so the power company in the area, and they want you to figure out how you should staff the call center, because people are going to be calling, either telling you that their power is out for a specific address, or they want to know when is it going to come back so they can plan accordingly. And so you, as the manager, need to decide who you should staff. And so one objective is you want to not have your customers waiting on the phone line too long. So you want to staff a lot of people in that respect to have maximum responsiveness. So a short wait time, short on hold time. So we're going to call that maximizing responsiveness. On the other hand, you have a boss and probably a budget that you have to stick to. And so you don't want to staff a bunch of people that, then are sitting there doing nothing when no calls are coming in. So you want your workers to be efficient, meaning that they're actually doing work and they're busy during their time while they're getting paid. And so we're going to call that objective maximizing efficiency. So these are conflicting objectives, because obviously if you want to maximize responsiveness, you're going to staff a whole bunch of people, and at certain times when the call volume is not very high, they're going to be sitting around doing nothing, waiting for the calls to come in. And so that's not very efficient. So we have two different conflicting objectives, and we want to decide how to answer this question. So to do that, we're going to create this efficient frontier of points that are not dominated, meaning that if you move from the efficient frontier, you have to do worse in at least one objective, and points along the objective, you do worse in only one objective here. So just details of the problem, that was the main problem, but some details. Here we're going to do a small example where we have 7 workers, and we're going to have 7 binary variables that it would equal 1 if you desire to hire a worker for that day, 0 otherwise. And so here's our 2 objectives. We're going to have responsiveness, so these are a measure of how responsive each of these workers are. A higher value means they're quicker and more responsive. So maybe they have better training, they're able to answer questions quicker, that kind of thing, which will make them more responsive. We then have a constraint here that is, you only have enough equipment to set up a certain number of people or spaces, and so we have here 15, and each of the workers take up different amounts of equipment, or maybe they only want to work a certain amount of hours. So this is a constraint here that's restricting you from taking certain types of, taking all of your workers in that respect. So, and then the last here is defining my variables as binary. Then I have an efficiency problem where I have the same constraints here, this less than or equal to 15 in my binary variables. However, my objective has changed. Here I care about efficiency, so maybe somebody isn't that responsive, but we don't require to pay them that much. So they're a younger worker, not that experienced, so they don't have as much pay, which would mean less responsive but more efficiency, because you're getting more for your money, essentially. So here's the values for the 7 workers on efficiency. So we're going to take these 2 problems and plug them into Excel. So here I have my 7 variables, x1 through x7, and this is similar to what Professor Sharkey posted in class, or went over in class. Here I have my responsiveness objective, and so all I've done is taken my different coefficients of the objective function and put them here. Then I've also done efficiency and done the same thing, where I've just put in those values in corresponding to the column that variable is. Now I have my constraint here, so it has to be less than or equal to 15, and then I'm going to have my decision variables here in green. So they're going to be 1 or 0, and whether I want to have that person working or not. Here I've also added, in this J column, I'm taking the sum product, so I'm just taking this responsiveness row times the decisions. So that would be the calculation. So that would be like 25 times whatever x1 assumes, 67 times whatever x2 assumes, and so on and so forth. And so that's my true objective for responsiveness, and I do, let's switch around, do the same thing for efficiency, and then here I'll use this for my constraint to say that this value here, J7, is less than or equal to 15. What Professor Sharkey then did was explain how we can use weights to do my efficient solutions. So I'm going to first start here. I have a weight for my first objective and then a weight for my second objective. And so all I've done here is, since we're dealing with 2, I just set my second weight to be 1 minus my first weight. So I just have to type in one number instead of 2. And then this objective here is what I'm going to use for solver, because I want my true objective to factor in both of those. So it's essentially how much weight should I put on this objective times its objective function value, plus for the other objective, its weight times its objective function value. And so that's what I've calculated here. And so then when I go, I need to decide on my weights. So I'm going to first look at just a high, I want to look at my extreme points. So if I only cared about responsiveness, so a weight of essentially 1, here I use 0.99 in case there's multiple optimal solutions. So I want to give that extra benefit to efficiency if there are multiple optimal solutions. And then I'm going to do just the opposite and then show you how to do a quicker way or more educated way to find your efficient solutions. So it's just a search technique. So first here I'm going to do 0.99. I'm going to set this up in solver. Oh, and that flipped around. Okay, there we go. So here I'm going to have my objective set to this value, M4. I want to maximize. My changing variables are here, what I've highlighted in green. So these are the binary decision variables. I then have 2 constraints here that I've already added. That I've said these binary decision variables are set to be binary. And then this calculation of my constraint, so this value J7 has to be less than or equal to K7. And so because I've put this in, I can now just solve. These 99 and 0.01 is already calculated. I'm going to do simplex and solve. So it might take a little bit of time because it's integer. Oh, it flipped over again. Okay. Because we have integer variables. So here I want to track my solution. So for a weight of 0.99, we see that we're going to hire workers 1 through 4 and not 5, 6, 7. And so let me just track this. So I'm going to copy here, paste this as values, and then track what my objective function value is. So 207 and 195. So here's like the solution values. That's what objective 1, or the responsiveness objective, and that's what efficiency objective. And I'm just also going to track what the first weight is here, so 0.99. So now I'm going to do just the opposite. So I'm going to try 0.1 and the other goes to 0.99. All I have to do now is do solver and solve. I already have it set up. All I'm doing is changing these weights. So again, I get a solution. It's different. So we do have conflicting objectives because they get different optimal solutions. So here I hire workers 1, 3, 5, and 6. And my objective function values are 125 and 252. And this was for 0.01. So here I'm just tracking like the weight of the first objective, and I know the second objective is 1 minus that. And so if we look on a number line, we've evaluated, so if our weights take a weight between 0 and 1, which I'm making that assumption here, you can normalize your weights if you have it between 0 and 10 to be like what percentage is that weight of the total number of weights. So I'm solely looking at weights between 0 and 1. And so here if I look at just what has been explored for weight 1, the weight of the first objective, so this value right here, I've looked at here 0.99 and 0.01. But this whole area here I haven't explored. So if you wanted to, you could go through and march, just constantly, start at 0.01, increase it a little bit, and go on. But you're going to get sometimes the same solution. So for 0.01 and maybe 0.02, you're going to get the same exact solution. Or possibly you could get the same exact solution. So we're going to try to eliminate you doing lots of different solving in order to, reduce the time needed to solve the efficient frontier. So we've taken the endpoints. So now let's explore what the midpoint is. So I'm going to look at 0.05 and we'll see how you adjust. So that's about the center there. So, and we'll see how the ranges become smaller. So now I'm looking at 0.05. All I have to do is tool solver, solve this. So I found a solution. The first thing you need to do is say, is this solution, so the decisions that it has it already been an efficient solution here? So I get 1, 3, 4, 5. So first thing I notice that this hasn't been found yet. So I'm going to put it in my list of efficient solutions. So I get an objective function value of 190 and 220, and this was for a weight of 0.5. And so now when I look back to my number line, I've explored 0.01, 0.05, and 0.99. So we're essentially doing, if you know what it is, a binary search. So I now have this range of values that I haven't explored and this range of values I haven't explored. So I could take 0.25 or 0.75. It doesn't really matter what you do next. I'm going to first try 0.75 and see what it looks like. 0.75, and I'm going to solve. So here I notice so it's solved for 0.75, and my solution here is that I get 1 through 4. I want to hire 1 through 4 for this particular day. What I then notice is that this solution has already been found for a weight of 0.99. So that means that any weight between 0.7 and 0.99 will get this efficient solution, 1, 1, 1, 1. 1 through 4 will be 1 and the rest will be 0. So here I looked at 0.75, and because 0.75 and 0.999 all have the same solution, I know that this whole range here is the same solution. So I'm just going to box this off and say these are all the same solution. So let me just color this a certain way so I know that these are all the same. So I don't have to reevaluate any of this range because 0.75 and 0.99 get the same exact solution. So now I'm going to go over here and do 0.25 and see what that then looks like. So here, 0.25. I'm going to solve. So I found a solution. First thing I need to ask myself is, has this solution been found? So I get 1, 0, 0. So we see here I don't have this solution yet anywhere. I'm going to paste this to my set of efficient solutions. I get 160 and 247, and this was for weight 1 of 0.25. So that's unique. Now I have 3 ranges that I haven't explored. So I can take any of the different ranges. So I'm just going to go left to right. So I'm going to take the midpoint here of 0.25 and essentially 0. So here I'm just going to do equals 0.25 divided by 2, that midpoint, which is 0.125. I'm going to mark this down. And I'm going to solve here. So essentially, I'm searching for either unique new solutions or solutions that then match a solution I've already found. And so here I find for a weight of 0.125, I get the exact same solution I get for 0.25. So I don't need to add it new to my set of new efficient solutions, but I am going to block off a range here because I know for this entire range from 0.125 to 2.25, they all have the same exact solution. And it's different than this solution, so I'm just going to color it a different color. So there, now I still have 3 ranges I haven't explored. I'm going to take, do like a greedy approach. I'm going to explore a bigger range. So I'll explore this 0.25 to 0.5 range. So I'm going to take the midpoint of those. So I'm going to take the midpoint of 0.25 plus 0.5 here divided by 2, which is 0.375, and I'm going to solve. So I found a solution for this, and what do I notice about it? Again, I get the same exact solution as I did for 0.25 for this 0.375 because I have, the 1, 0, 0, 1, 1, 1, 0. So here I can add, let's add, what was it, 0.375, I think? Yes. And I know this same solution also handles this range. So I'm just expanding by taking this bigger, the midpoints of these ranges, I'm blocking out a whole bunch of stuff that I know information about. So because 0.375 is the same solution as 0.25, I don't have to test for any of these solutions in the middle here. If I was just marching along, I would have to keep on marching along because I don't know when this 0.375 was actually occurring. So now I'm going to, again, look at, so I know about 0.5. I know 0.5 is different than this, and I know 0.5 is different than 0.75. So essentially I have 3 ranges. I have this range here, and then this last range. So I'm going to look at the biggest range again. So I'm going to take the midpoint of 0.5 and 0.75 and see what I can find. So that ends up being 0.625. I'm going to solve. Okay, and what do I notice about my solution? My solution here is 1111, and that matches what my solution is for 0.99. So for a weight of 0.625, I know that it has this same solution as this orange one because it is the same as 0.99, same as 0.75. So I just blocked out a whole bunch of stuff that I didn't previously know the information about, but now I do. So again, I have still 3 ranges. I'll just continue here, the 0.5 to 0.625. So I'm going to take the midpoint of those two, 0.5 plus 0.625 divided by 2, 5,625. I'm going to solve. And what do I notice? I get 1011100, which is exactly the same as the 0.5 solution. So for a weight of 0.5625, so let's just add this. $5,625. Is that right? Correct? Yeah. Okay. That these two have the same exact solution. So I'm just going to copy a box here and size it correctly. So for this range here, they all have the same exact solution. So let's just color it green for now. So now we know there are 4 distinct solutions that we found. You know, the 0.1 here, we haven't yet explored this range to see how far out it goes. We have this solution, which we know is true for all of these weights for objective 1. We don't know about this range here. We do know about this range. We don't know about this range. So again, we have 3 ranges that we could explore. Let's go, because we don't know much about this 0.01, let's take the midpoint here of 0.125. So we're just going to take 0.125 divided by 2. Ooh. And see what then I get. So here I get a solution that is exactly the same solution that I got for 0.01. So for 0.0625, so let's add that. This has the same solution as 0.01. And so let's color this a different solution. And so now we see, again, we still have 3 ranges we haven't explored. This one looks the biggest, and we'll look in there. So there still could be unique solutions in these ranges that we haven't found. Or it could be that you'll find the breaking point where these 2 solutions meet, and that trades off between one solution and the other. So here I'll look at the different, 0.5 and 0.375. So 4.375. And eventually you'll get to a point where the ranges that you haven't explored are really small. So it found a solution, and this solution is exactly the same solution as 0.25. So for 0.4375, it has the same exact solution as 0.25, which is the same for this whole range here, and so we expand it there. So again, we have 3 ranges that we haven't explored. I hope by now you at least get the pattern of what you do. So to explore this range, you would take the midpoint of these 2 values. So you take 0.125 plus 0.0625 divided by 2, plug it into the weight, do solver, and then see, does it equal this solution? Does it equal this solution? Or is it a new solution altogether? And you would do it for all of the ranges you have not yet explored. So this range, and this range. And by using this visual where you're color coding what boxes you have or what ranges you have explored, it makes it a little easier to see and visualize where your solutions are for what weights. And so I'm going to stop here. Obviously, I'm not done with the entire efficient frontier because I haven't explored all the ranges, but like Professor Sharkey mentioned in class, sometimes it's beneficial to only have a couple points on your efficient frontier if you're going to present it to a manager who then, he or she does not want to be overwhelmed by, hundreds of points on the efficient frontier that are all really close, that will then hinder the boss's ability to make decisions on what efficient point should I pick over another efficient point. So here we've come up with 4 different efficient points that then you can see and make your decisions accordingly. So I hope this helped in, again, seeing how to create the efficient frontier. And so if you were going to map this, I don't have a visual, but essentially you would have like your responsiveness on one axis and efficiency on the other axis, and then plot the points, the objective function values of the points here to see how your efficient frontier curves. So again, feedback is appreciated to know if you like the video or not like the video, and comments as well. Just make sure you hit submit even if you're just not doing comments, if you just click 1 through 5 in the helpfulness. And feel free to request other videos. And if you watch this before Hurricane Sandy actually does come, stay safe, and maybe see you on Thursday. Thanks.